I'm actually going to move down a little bit in the architecture. So this is a high-level view of the architecture of OpenMM. It's based on a layered architecture where each layer is built on the levels above it. So at the very top level, we have the application layer. This is a high-level Python code that allows you to just use OpenMM as an application to run simulations. But there are all these other layers below it. Down to at the very bottom, we have the actual computational kernels that do calculations. I'm now going to move down one level for this talk and discuss what we call the OpenMM public API. Up until only about a year ago, that was the highest level of OpenMM. OpenMM was just a library. And then in version 4.0, we added the application layer on top of it. But we still have all these other levels. And in this talk, I'm going to move down and talk about the public API and what you can do with it. So you might be wondering, why would I want to make use of this API, the one that's a level below? Well, if you're an application developer, someone who's not going to just be using OpenMM to run simulations, but you're writing your own applications and you want to use OpenMM within your applications, this is how you do it. The public API is very specific. Oh, by the way, API stands for Application Programming Interface. Occurs to me that some of you may not know that, but an API just means the interface, the set of functions, whatever that you use to communicate with the library. So if you're writing an application and you want to use OpenMM in your application, this is how you do it. This is the interface you use. Now, if you're interested in working at the higher level of just running simulations, you don't have to know most of what I'm going to talk about, but it's there. All of the things I'll be talking about are available for use in your scripts if you want them. And there is a huge amount that you can do with it. So while you don't actually need to know about most of what I'm going to talk about here, it's very, very useful. And once you get a little more advanced, you'll find that there's a lot you can do with it. So let's talk a little bit about how we designed this interface, this API, because we had some very specific goals in mind when we designed it. Now, the first thing is that we wanted it to be very simple. We wanted it to be easy to learn and easy to use, because we wanted lots of people to use it. And we knew that if it wasn't easy to learn and easy to use, that would limit how many people would use it. But when I say easy to use, that means more than just it's easy to learn what the functions are and to call them. It also means that it needs to be easy to use correctly. Because molecular dynamics is a very complicated field. There's a million features out there. There's a million ways you can run a simulation. And frankly, a large fraction of those ways are not the best ways of doing it. And we want to design the interface in a way that we will try as much as possible to make it easy to use correctly, that it will steer you towards doing things in reasonable ways. If you just do things in the obvious way, as much as possible, that should be a reasonable way of doing it. Another goal was that we wanted it to be very extensible. Like I said, it's a huge field. There's a million ways of doing things, and we cannot hope to ourselves implement and provide every single feature anyone might ever want. So we wanted to make it very easy to extend it, so other people could add new features to OpenMM, both by writing plugins, writing your own code that just plugs into the architecture, and also by using custom integrators, custom forces, some of the features I'll talk about later. It also is designed to make it very easy to support new hardware platforms. Well, easy is relatively speaking. Of course, if you want to support a new hardware platform, you need to actually write all the code that runs on that hardware platform, which is very hard and is a lot of work. But nonetheless, the architecture is designed so that that code can be written and can seamlessly plug into the architecture. So when someone goes and runs it, it becomes very easy for you as an application developer to just make use of that. It's very important that it can be implemented efficiently on a variety of hardware platforms. This actually is a very non-trivial thing to do because different types of hardware are very, very different from each other. And it would be very, very easy to create an interface that was simply impossible to implement efficiently on some types of hardware. because we wanted to support everything from single core, single CPU cores, multi-core, multi-processor CPUs with non-uniform memory access, GPUs, specialized accelerators, not to mention, we don't currently support parallelization on clusters where we, split one simulation over multiple nodes on a network, but we do hope to support that eventually. And we want an interface that can be implemented efficiently on all of those. And there are some very easy things that, if you're used to writing for just a single processor on a single computer, that you might just be tempted to do. Like, how do you ask? You want to be able to ask, what is the position of a certain atom? Well, an obvious thing to do would be have a function, get atom position, where you give it the index of an atom and it returns the position of that atom, which is going to be a really, really slow function on certain types of architectures. Like on a GPU, the positions are actually stored on a separate device connected to your main computer by a relatively slow PCIe bus. So getting information over that bus is really slow. But even that is not as bad as a cluster where the position of a particular atom might not even be present on the node that your program is running on. So if we just provided that function, and then a very natural thing would be to write a loop over all atoms and ask for the position of each one, that would simply be impossible to implement efficiently on many types of hardware, like GPUs or like clusters. And so we intentionally designed the API so that you can't ask for the position of a single atom. The only thing you can do is ask for a whole lot of data. You say all at once, what's all the data you're going to want? Like, give me the positions of all the atoms, and maybe while I'm at it, I also want the velocities and I want the force acting on every atom. And then we can, in batch, collect all that information and transfer all that information together. So we had to think about all these things while we were designing the API and come up with an interface that could be implemented efficiently on many types of hardware. And one other goal we had is we wanted it to be easy to incorporate into existing code bases, because we wanted people who have existing code bases to be able to plug OpenMM into it. And this had a lot of considerations, that it had to be something that you could easily plug in that doesn't require that OpenMM be driving the whole show, but something you can easily call out to from whatever code you've already got. A little bit on our choice of what languages to use in implementing it. So the OpenMM API is written in C++. It is natively a C++ API. However, we provide wrappers for Python, C, and Fortran. So you can quite easily invoke it from Python, from C, and from Fortran. And for the most part, they are complete versions of the API. Anything you can do from C++, you can do from those other languages. The only exception to that is that plugins can only be written in C++. So if you want to write a plugin that implements some new feature within OpenMM, you're going to have to write some C++ code to do it. But pretty much anything else you can do in any of these languages. All right, I'm now going to give you a whirlwind tour of the complete OpenMM public API. And I'm going to do it in 3 slides, okay? So there's not all that much here really to see. So the first class that we're going to talk about is called System. It's one you've actually already seen. You'll remember that we called create system in those scripts and it created a system object. Well, so system is actually a class defined at the layer of the public API, the one down a level below the application layer. And it just defines a collection of interacting particles. It defines a little bit of information about them, like the mass of each particle. It can define distance constraints to say that these 2 atoms must always remain this distance apart. And it has a few other basic things like that that it can define. But then it also contains a list of force objects that define how do these particles behave, how do they interact with each other. And I will get to force objects in, I believe, the next slide. Another very important class is called context. Context stores all the information about a simulation that you're running, like the position of every atom, the velocity of every atom, and it contains a bit of other information as well, like the time and the current size of your periodic box and some things like that. In the examples you saw, we created a class called simulation. Simulation is basically just a thin layer around a context. In fact, there were even some lines in there where it called simulation.context to just go to the context directly and make some calls on that. But basically, context is the class that contains all the information about a simulation that you're running. Force is a very important class in OpenMM. It's an abstract class. So force just sort of defines this general interface for forces, and there are many, many specific subclasses, specific types of forces that implement particular interactions. Now, actually, the name force is a little bit misleading because the force class can actually be a bit more general than just applying forces. It can also implement like thermostats and barostats. Unfortunately, we've never been able to come up with a better name than force, so it's called force. But there's a list of things that a force object can do. So it can apply forces to the objects, to the particles in your system. And of course, because it's applying forces, that means it also needs to be able to add a contribution to the potential energy. It can define adjustable parameters that are, just parameters that you can change over the course of a simulation, like, if you're using a force that implements a barostat, it's going to define a parameter called pressure so that you can change your pressure. But it also has the ability to modify the positions, velocities, and parameters at the start of each time step. So that, for example, a force object that implements a barostat is going to be wanting to go in and, scale your periodic box and change your particle positions. So don't worry too much about the details of this. All you need to know is a system contains a list of force objects. Those force objects define particular interactions like harmonic bonds, non-bonded forces, things like that. And you add forces to your system in order to say what are the interactions being applied to your particles. Any questions? I hope I'm not going too fast. Does this generally make sense? Yeah?
You said that it can apply these at every single time step?
Yeah.
And is that just done by default or only if it's actually changed?
No, it does this automatically. A force has the ability to do this. Whether it actually does or not is completely up to that object. Integrator is another class that you have already seen. It is defined, again, at the level of the public API, so a layer below the application layer. But when you're using the application layer, you still make use of this class. The integrator advances the system through time, and we provide, this again is another abstract class, so you saw a particular subclass of it called Langevin integrator that implements a Langevin algorithm, but we have a number of other integrator types like Verlet if you want to do a constant energy simulation. We have a Brownian one. We actually have a few variable step size integrators in there. But basically, integrator, abstract class, advances your equations of motion through time. Different subclasses of it implement particular methods of advancing the equations of motion. One more very important class, and you'll see this is slide 3 of 3, so this is our very last one, is called state. A state is a snapshot of the state of your system. So context is sort of this mutable, changing thing that is constantly changing as you run your simulation and always has what are the current values of all of your positions, velocities, etc. Well, state is the way that you query that. I said that you always get information in bulk. Well, the way you do that is to go to your context and say, give me a state object. And the state object is immutable. So once it creates this object, returns it to you, and then it's just an immutable record. It's a snapshot at the moment when the state was created. What were the values of all your state variables? This is the only way to access your positions and velocities is by creating a state object. And I also mentioned that when you create the state, oh yeah?
Can you restore the system to a particular state?
Oh yeah. That when you create this, you tell it specifically what information you want so it can efficiently go and get just the information that you're going to want and package it all together in the state. So optionally, it can include what was the force on every particle, what were your current kinetic energy and potential energy, and some other things like that.
Did you get the state at any particular step during the simulation?
Yeah, anytime you want.
So your context must be big ass.
Yeah. The context is all the changing things, and the state is just a snapshot.
So the question is state something you only get at a specific specified time, or you say if a certain condition happens?
So at the level of the public API, you just call getState on your context. So the context has this method called getState. You call it, you tell it what you want, it gives you a state. You call this whenever you want. So you might tell your integrator, simulate 100 time steps, and then you say, okay, give me a state. You might do something with it. Now, in the application layer, it wraps your context in this other class called simulation. And the simulation only adds a few things, but the most important thing it adds is this reporting mechanism where you can add, like we added a PDB reporter to it. So the simulation actually just adds this little bit of extra logic so that when you say simulate for 10,000 time steps, it doesn't just simulate 10,000 time steps. The first thing it does is go to all the reporters and say, okay, when's your next report? When's your next report? Oh, I see my next report is going to be in 50 time steps. So I won't really do 10,000 time steps. I'll do 50 time steps. Okay, now we're where you want. You said you've got a report. Go ahead, do your report. You're done? Okay, let's look. Okay, I see our next report will be in another 100 time steps, run another 100 time steps, etc. So simulation just automates that process for you. But if you're working at the lower level of the public API, you would basically do the same thing yourself. You would say, run 100 time steps, get a state, you do whatever you want to do with your state, then run some more.
So then, just following on his question, if you wanted to run the simulation until something happened, the only way to do it would be just to periodically check the state, and each time run that loop, let's say every 100 time steps, check to see if the condition has been met.
Right. Yeah, if you're working at the public API. If you're working at the application layer, an alternative way would be to write a reporter that automates that. Well, let's look at some actual code. Now let's just dive in. So this is just going to be really simple code just to show you how it works and to give you a flavor for what this interface looks like. So we're going to create a system object. So system equals system, just basic Python notation for create a system object, assign it to a variable. Excuse me. If you were working in C++, it would look almost identical. It would be system equals new system semicolon, but almost identical. We're going to want to add some particles to the system. So we're just going to loop over our list of particles. Particles, I'm just assuming you've already got a variable here that lists off what all your particles are that you want to add. And for each one, we're just going to call add particle on the system. And there's one argument that you pass to add particle, which is the mass of the particle you want to add. So you loop over all your particles. You call add particle for each one. Now your system has a bunch of particles in it. Maybe you want some distance constraints, so we're going to loop over constraints, and you're going to call add constraint for each one. And the things that you pass to it are the index of the first atom involved, the index of the second atom involved, and what should be the distance between those two. So again, this is what you'll see. The whole interface looks very much like this. Constructing all your things, you just are going to loop over something and call add such and such to add a whole bunch of something. So here we're adding a bunch of distance constraints. Okay, so we've got a system, we've added some particles, we've added some constraints to it. They're not going to do much unless we add some forces. So let's say maybe we want some harmonic bonds. So this is, a standard functional form used in a lot of MD force fields to implement, a bond between two atoms, which we just model as like a harmonic spring. So there's a class called harmonic bond force, which is a type of force. So we're going to create a harmonic bond force, and we are going to add a bunch of bonds to it. So how do you think we do that? Well, we're just going to have a loop over bonds, and for each one we will say add bond. And this one, for add bond, what we pass to it, index of the first atom, index of the second atom, what is the equilibrium length between the two, and what's the spring constant. So we're going to loop over our bonds, add each one to our bond force, and then finally we're going to call add force on the system to say, okay, by the way, here is a force object, add it to the system. So this force should be allowed to apply forces to the atoms in my system. And there are lots of other forces. So, if this were a real molecular force field, we would have a term for angles, we would have a term for torsions, we would have non-bonded interactions. And each of these is just a different force object. And you can look up exactly how you create and set up each one of these, but they all look very, very similar to the code I've just showed there. All right, so let's assume we've done that. We've created our system, we've got our particles, we've got our constraints, we've added all our forces. Now we're ready to actually simulate it. Well, to simulate it, we need an integrator. So we'll create our Langevin integrator, which looks a whole lot like a line you already saw from your scripts, just like when you created your Langevin integrator before. And now we're going to create our context. So this, again, is just analogous to where we created a simulation in the previous script, because a simulation is just a wrapper around a context. So we say, OK, create a context for this system and this integrator. So we're going to use this integrator to create this system, or to advance the equations of motion for this system. We call set positions, exactly like we did before. And maybe we're also going to set the velocities. In the previous example, I didn't actually do that, which meant the velocities were all just started out as 0. But maybe you've got some initial velocities you want to set. And then we call step on our integrator. And that will run for 500 time steps. And at the end of 500 times, at the end of that line, it's finished simulating 500 time steps.
Question?
Yeah.
So in the context here, you're not specifying units, whereas in the example we did. Is that
Yes.
something that has a nice default?
I will get to that later. Yes, I will have a number of slides on units. So we've just done a bit of simulating. Now we want to retrieve state information, so maybe we want to analyze them to see if some condition is met. Maybe we just want to write them out to disk, whatever. So we're going to call getState on our context. And that will create a state object and assign it to this variable called state. And we have to specify what information we want the state to include. So we say get positions equals true and get velocities equals true. So this state is going to contain positions and it'll contain velocities. We could ask for other information like energies or forces or things like that, but in this case we aren't. And now we've got a state object, and we can call get positions on it to get that list of positions. So here I've just done this completely trivial thing of just looping over all the positions and printing them out, just to show you an example of what the code would look like. In practice, you'll probably do something different. So this is pretty much the complete code to run a simulation, except that, of course, in this case, I've just assumed we already had all this information ready to add. We already knew what our list of particles was. We knew what the position was. We knew what all our bonds were. If you're actually writing a program, of course, you're going to need to provide that information. You'll get it from wherever. Now, if you're working at the application layer, we provide routines to do that. The PDB loader, the force field class, etc. And in fact, all this code that you've seen here, like this, where it's creating a system, adding particles, adding constraints, adding bonds. This is precisely what the force field class was doing. You can look up the source code for the force field class, and you will see code in it that looks almost exactly like what's here. So it just does this for you. It knows how to load in a PDB file and load in a force field description and build the system from it. But for your own programs, maybe you'll be getting that information from somewhere else. One other very, very important concept here is what we call a platform. The thing to understand here is that this API defines an interface. It doesn't say anything about the implementation. We have this thing called a harmonic bond force. Harmonic bond force says, OK, these are the functions you can call. And it also defines this is the mathematical form of the force that should be applied. But it doesn't provide any code to actually apply that. The actual code that implements it is provided by something different that is called a platform. And in particular, a platform provides the implementations of all these different features. OpenMM comes with 3 platforms. In the future, there could be others. It's even possible for you to write your own. It's a lot of work to write a complete platform because there's a lot of features that are there to implement, but it's all completely modular. Every platform provides an implementation of all these features. So we provide three. The first is the reference platform. It's written in C++. It's really slow, but that's intentional. It's not there for really to use in production. The goal of the reference platform is that you can use it as a reference to look at the code to see, okay, how is this force supposed to work? Also, it's something we can compare to make sure that the other platforms are giving identical results to the reference platform. And intentionally, in fact, we very intentionally have not made any optimization in the reference platform that would reduce the simplicity or the readability of the code. So it's really slow, but it's supposed to be. It's not there for production use. It's there to show how the code is supposed to work. And then we have OpenCL and CUDA platforms. These are the ones that you would actually use in production. So both of them can run on GPUs. CUDA, of course, is an NVIDIA technology, so it only runs on NVIDIA GPUs. OpenCL can run on both NVIDIA and AMD GPUs, and it also can run on CPUs. So if you don't have a GPU, but you want to use OpenMM to run on your CPU, you would want to use an OpenCL implementation that works on CPUs. AMD's implementation can run on CPUs, and Intel also has one that we don't yet support, but in OpenMM 5.1 will also support Intel's implementation. So to select a platform, just the platform is a class, but it has a static method called getPlatformByName. So getPlatformByName OpenCL will return the OpenCL platform to us. And then when you create a context, you can pass that platform as the third argument. So in the other examples, we didn't specify a platform, and again, it just tried to guess what it thought would be the fastest one. But you can just tell it, this is the platform I want you to use. And the same is true when you create a simulation object. You can just give it a platform as the next argument to tell it, this is the platform I want you to use. Another thing that you might want to do is find out, maybe you didn't specify one, you let it pick, but you do want to know what platform it picked. So on your context, you can just call getPlatform and then call getName on that platform. And then by doing that, you can just print out, okay, what's the name of the platform I'm using? I just want to know. One other thing you might want to do is find out just what are the platforms that are available. And so the platform class just provides an interface that you can query that. You can ask it, get num platforms. How many platforms are available? And then you can get the platform by index and query each one, what's the name of this platform? So that's just a way that you can get a list of what are all the platforms that are available. Okay. Documentation, very, very important. All the API documentation, it's available. It's if you look in your docs folder where you installed it, you'll find two files called C++ API reference and Python API reference. Bring those up in your web browser to get a nice browsable interface to all the API documentation. If you are running on Amazon, so it might not be so easy for you to do that, the same documentation is also online. Just go to the OpenMM downloads page and you'll find links to it right there. If you're using Python, there's also a couple of commands just useful to know about, because you can do these like from a Python command line. You can type called the help function to bring up that same documentation for any class or any method. So if you say help parentheses context, it will just print out for you all the documentation for the context class. Or you can say context.getState to say I just want the documentation for the getState function. But you can also pass it just an object to say, give me the documentation on this class. So if we like help simulation.context, that would be another thing that would give you the documentation on the context class. I mostly find it easier to just use the web browser, but this is a nice thing to know about. Python also has a very convenient function called a dir, short for directory, that you can give it any object, and it'll just list off to you every data member, every field, and every method of that object. Just if you find yourself doing a lot of Python, these are good things to know about. The C++ and Python APIs are almost identical. In fact, I mean, the Python API is generated automatically from the C++ one. It's not like we wrote it by hand. We use this tool called Swig that takes the C++ API and generates a Python API from it. But there are a few differences that you should know about, just some places we changed to make it either to improve it or to make it just more of a native Python API. One is the getState function. In the C++ version of it, the thing you pass to it is a set of flags that you OR together. So you say state positions and OR that with state velocities to say I want positions and I want velocities. This is a very normal sort of interface for a C++ function. But for Python, that sort of thing isn't done much. More natural thing is to use these Boolean arguments, like we showed, get positions equals true, get velocity equals true. So we did that just to give it a more natural Python API. A similar thing is there's a bunch of functions that return multiple values. Like if you have a harmonic bond force and you want to ask it, give me all the parameters for this particular bond, which means, what are the indices of the two particles, what's the equilibrium length, what's the spring constant. Well, C++ doesn't support just returning multiple values directly. So what you do is you create a bunch of variables to hold those, and then you call the function and pass it those variables by reference, and that function will store the values into those. This is just the way you do this sort of thing in C++, but it's not the way you do it in Python. Python does support multiple return values, and so all the functions that are of this flavor, where it's f.get bond parameters. The C++ one, you create variables, you pass those variables, the function stores it into it. But in Python, you just give it the index, and it will return those same values to you in order, just as multiple return values. So again, it's a little thing we did just to give it a more natural Python interface. One more difference, what you were asking about. In Python, quantities have explicit units. Why did we do this? Well, there are a lot of different unit systems that are widely used in molecular dynamics. It would be nice if everyone used the same units, but sadly they don't. For example, do you measure time in picoseconds or femtoseconds? Some do one, some do the other. Do you measure distance in nanometers or in angstroms? If you survey the MD packages out there, you'll find they're split between the two. Some measure distance in nanometers, some measure it in angstroms. What about energy? Some programs like to measure energy in kilocalories per mole. Others measure it in kilojoules per mole. And here's the really sad thing. You are going to make mistakes in units, and this is going to produce bugs in your code. I absolutely guarantee it. I know you think, I'm a smart person, it's just units, it's just some simple conversion factors, I can handle this. And I'm sorry, I know you think you are, and I know you really are a smart person, and you're still going to make mistakes because humans just aren't well designed for handling this sort of thing. And you are not alone in this. Everyone makes mistakes. And there have been some very famous examples of this. Perhaps the most famous was the Mars Climate Orbiter, which in 1999 crashed into Mars. It didn't execute its landing sequence correctly, and a cost of $125 million down the drain. And it was eventually determined that this failure was caused because someone made an error in unit conversion in some of their code. Another very famous case was Air Canada Flight 143. Back in 1983, Canada was in the middle of converting over from imperial units to the metric system, and someone in converting the instructions for refueling airplanes made a mistake in conversion, and they didn't put enough fuel into the plane, and it ran out of fuel in midair. Thankfully, the pilot of this airplane had experience flying gliders, and he was successfully able to coast to the ground, and no one died. But errors in unit conversion do happen. Human brains are just not well suited to do this sort of thing. And therefore, we're trying to help you out and save you from some of these errors. So, if you are working in the Python API, we provide an explicit unit system for you. It's really easy to use. You've already seen how to use it. When you write any number, just multiply it by the units. 5 times nanometers means 5 nanometers, exactly like you'd expect. Compound units, no problem. 9.8 meters per second squared, 9.8 times meters divided by seconds squared, and we'll just handle this for you. Once you've got a quantity with units on it, it's really easy to convert it to any other units. You just call in units of and give it the units. So we define 5 to be 5 nanometers. If you wanted an angstroms, just say 5, or size.in units of angstroms, 50 angstroms. This is still a quantity object, which is this thing that combines a number with a set of units. At some point, you may need to pass it to some other function that just needs a pure number. So you can also call size.value in units angstroms, and this returns just a completely ordinary number, 50, which is the value of that in units of angstroms. Generally, leave it as a quantity as long as you can, and just convert it to a unitless value at the last moment when you absolutely need to. When you do math with quantities, conversions just happen magically. You don't have to think about it. 5 nanometers plus 25 angstroms equals 7.5 nanometers. You don't need to do the conversion. OpenMM will do it for you. This is one of the places it will save you from making mistakes. You might try to get it to do something nonsensical. 5 nanometers plus 25 picoseconds. How do you add nanometers to picoseconds? Well, if your code didn't have units, it would just say, oh, 5 plus 25, that's 30, no problem. OpenMM won't let you do it. It will say, type error, cannot add 2 quantities with incompatible units, nanometer and picoseconds. This is another place. It will save you from making mistakes. You can apply units not just to numbers, but to any sort of numerical quantity, lists, tuples, NumPy arrays, no problems. Just multiply like your whole, a tuple by nanometers, and it will do it. You can also strip off units or do unit conversions on entire arrays at once. So like state.getPositions, we can just call in units of angstrom and convert that entire array of positions all at once. So units are optional, but highly recommended on input values. Anytime you're passing a value to an OpenMM function, we really, really recommend that you include units on it. That way, you don't have to worry about, did I remember to put my value in the right units? You just say, these are the units my value is in, and OpenMM will do whatever conversions it need. Also, output values that it returns to you will always have units on them. So when you query, what is the length of that bond? It will be a quantity, it will have units attached, and therefore, if you want that value in a particular unit, you can just say value in units or in units of, and it will give it to you in whatever units you want. That is the Python API. C++, not easy to implement this sort of unit conversion system. Excuse me, and we don't. There are some libraries out there that have attempted to create units systems in C++. It's really complicated. It really does weird things to your code. We decided not to even try to go there. C++ just isn't as well suited as Python for this sort of thing. So when you are using C++, all quantities must be in the default OpenMM units. Those units are, and you can find this in the user guide as well. Distance is in nanometers. Time is in picoseconds. Temperature is in Kelvin. Mass is in atomic mass units, also known as Daltons, also known as grams per mole. Energy is always in kilojoules per mole. And charge is in units of the electron charge, or I should really say the proton charge. There's a reason we picked these units. They form a consistent unit system. This is not true of many of the unit systems that you will find in other MD packages. For example, any package that measures energy in kilocalories per mole, not a consistent unit system. What are the units of force? Well, if you compute a force as the gradient of an energy, you will get one set of units. If you calculate it as a mass times acceleration, you will get a different set of units. And so packages that measure their energies in kilocalories per mole have to have all these weird conversion factors scattered through the code. It's a great opportunity to create bugs. And when you query them for a force, you have to think, what units is this in? We chose a unit system that is completely consistent, so a force is always a force, always the same units, no matter how you calculate it. So we've done our best to make things easy for you, but we still can't in C++. You still have to make sure that the quantities you give us are always in these units. We do define in one of the header files, we provide some conversion factors for you so that if you have something in angstroms and you want to convert it to nanometers or whatever, we provide some constants to multiply by, but you've got to be careful and it's up to you to do that. All right, which language should you use? Well, obviously, if you're going to be working at the level of the application layer, you're going to be using Python because that's the language it's written in. But for your own code, you've got your choice. Python, C++, and I didn't list C and Fortran. You can use those. I'm not sure I would ever recommend that to anyone, but your choice. But between Python and C++, Python's a lot faster to develop. It's a lot easier to write Python code. You can write your code a lot faster. It's much simpler. Python has this nice interactive prompt. You can just bring up a Python interpreter and start typing commands, which is very, very convenient for experimenting. And of course, it's got the explicit unit system. C++ has the advantage that it does execute faster, a lot faster. Now, most of the time, this isn't going to be an issue because all the heavy computations are getting done inside the OpenMM library, probably on your GPU. But if you're actually writing a lot of significant computations in your own code, they'll run a lot faster in C++. It's also much easier to call from other languages because Python runs inside an interpreter. If you want to invoke Python from any other language, you've got to actually spin up a Python interpreter, which is a complicated thing. So, if you're writing like your own library that you want to call from other languages, that'll be a lot easier in C++. And finally, if you want to write plugins, you have to do that in C++. Just one last thing. This is a diagram that basically maps out the relationships between all the important classes in OpenMM. It's a lot of arrows and diamonds and circles, but it puts a lot of information together into a very convenient form. Basically, here's the key to it up here. So all these green diamonds are classes that exist at the level of the public API. So all these things I've just been talking about: force, integrator, system, context, state, etc. So those are all the things that, like, if you're writing up your own program in C++ and you want to call OpenMM, those are the classes you can use. The circles are classes that exist at the level of the application layer. And they're actually in two colors. All the ones that are in gray are classes that basically are like wrapping a file on disk. So like an Amber Parm-top file, a PDB file, a force field file that is defined by an XML file that I think Li-Ping will be talking about that tomorrow. And then classes like simulation and reporters and topology are just other Python classes. And this just sort of shows you the relationships between these. I hope you can see this well, that like if you want to create a simulation, it requires an integrator, and it requires a system, and it requires a topology. And then this simulation creates a context object, and you can use that context object to create other state objects which contain this other information like positions and velocities. So this is just a schematic. I believe we've got this diagram up on the website. Anyway, so it's a very useful diagram just to try to wrap your head around a whole lot of information, just all these different relationships in a small amount of space.